Welcome to our comprehensive exploration of modeling theory, where we'll discover how algorithms transform carefully prepared data into intelligent predictive systems capable of solving complex real world problems. Machine learning modeling represents the core intelligence building activity where data transforms into actionable insights and predictions. This is where mathematical theory meets practical application, creating AI systems that can understand patterns and make informed decisions about new situations they've never encountered before. Modeling encompasses the complete process of selecting, configuring, and training algorithms to learn patterns from data, make predictions about new situations. This phase represents where data transforms into intelligence, turning static information into dynamic systems capable of reasoning and decision making. The modeling process requires careful consideration of algorithm selection, parameter optimization, training procedures, and prediction generation. Our modeling journey follows four interconnected steps that build intelligence systematically. Algorithm selection matches the right mathematical approach to your specific problem type and data characteristics. Model configuration fine tunes the algorithm's parameters for optimal performance. The training process allows the algorithm to learn patterns through mathematical optimization. Finally, prediction generation applies the learned knowledge to make forecasts about new, unseen data. Algorithm selection requires strategic thinking about matching your specific problem with the most suitable mathematical approach, much like choosing the right tool for a construction project. Different problem types, classification, regression, or clustering require different algorithmic families. We consider factors like data size, interpretability requirements, accuracy needs, and computational constraints. Linear regression provides interpretable results for straightforward relationships. Random forests offer balanced performance across various problems. Support vector machines excel with high dimensional data, and neural networks handle complex nonlinear patterns. Model configuration involves fine tuning the algorithm's hyperparameters, the settings that control how learning occurs but aren't learned from data themselves. These configuration choices dramatically impact performance, much like adjusting a precision instrument before critical measurements. We optimize learning rates that control training speed, regularization parameters that prevent overfitting, architectural choices like tree depth or network layers, and convergence criteria that determine when training stops. Systematic approaches like grid search or Bayesian optimization help find optimal parameter combinations. The training process represents where learning magic happens as algorithms examine data repeatedly to minimize prediction errors through mathematical optimization. Linear models learn optimal coefficients through techniques like least squares, while neural networks adjust connection weights using backpropagation. This iterative process resembles gradient descent, systematically moving toward parameter values that minimize mistakes. We monitor training progress carefully, watching for signs of effective learning while avoiding overfitting where models memorize rather than generalize. Prediction generation represents the moment when our trained model demonstrates its learned capabilities on fresh, unseen data. Classification models calculate probabilities for different categories and provide confidence measures, while regression models perform mathematical calculations based on learned relationships to produce numerical predictions. The critical test is generalization, whether our model applies learned principles to novel situations, proving it captured fundamental patterns rather than simply memorizing training examples. The bias variance trade off represents one of machine learning's fundamental concepts, describing the balance between model simplicity and complexity. High bias models are too simple, underfitting the data and missing important patterns. High variance models are too complex, overfitting training data and failing to generalize to new examples. Our goal is finding the sweet spot that minimizes total error, the sum of bias squared, variance, and irreducible noise, creating models that generalize well to new situations. Consider predicting house prices using features like size, location, and age. We might choose random forest for its ability to handle mixed data types effectively. Configure hyperparameters like 100 trees with maximum depth of 10, train on 8. 100 houses to learn price relationships, validate on 100 houses for parameter tuning, and achieve a mean absolute error of $15,000 on our test set. This systematic approach ensures our model learns genuine pricing patterns rather than memorizing specific examples. Professional modeling follows several key principles that separate successful implementations from amateur attempts. Start with simple models and add complexity gradually to understand what drives performance improvements. Use cross validation with multiple train validation splits for robust performance estimates. Apply regularization techniques to prevent overfitting. Consider ensemble methods that combine multiple models for improved accuracy. Remember that thoughtful feature engineering often impacts results more significantly than algorithm selection. Now you got a very good overview of machine learning modeling. In the next session, we will learn about model evaluation. So guys, see you in the next session.